okay? And there are all these feedbacks that just are both the Greenland and the Arctic snowballing this faster and faster. Antarctica is the giant of this whole thing. It had much more ice. Greenland can put like 23 feet of ice of sea level rise if it all melted. It won't all melt, but some of it will. And the Arctic can maybe do another couple hundred feet. So, and we said, oh, it has a separate climate system, don't worry about it. Well, it turns out it's coming alive, and the increased wind shear projected by climate change is starting to move warmer water under these floating ice sheets on the edge of Antarctica and starting to thin them. At some point they will loosen and start to move away, and they're the plug, the champagne plug. When you take it out, everything comes pouring out. In addition, this January article in Nature that points out that, which we didn't realize, that Antarctica atmosphere has been warming at the same rate as the rest of the world, and about 0.2 degrees per decade. That's very disturbing. Okay? Because the IPCC blew it, we, our science panel in Miami-Dade County put out a statement in September of that year, finally in January, saying that with what we're seeing in the Arctic and Greenland, we should expect at least a further 1.5 foot rise of sea level by within 50 years, and at least 3 to 5 feet by the end of the century. The difference between 1 to 2 feet in the coming century and 3 to 5 feet is all the difference for South Florida, and it's not a pretty picture. Here's South Florida. I'm sorry I don't come up to Broward County, but this gives you the idea. Here's South Florida today. A 2 foot rise of sea level will overwhelm much of the coastal wetlands, and probably will move sea level from the present shore of Florida Bay up to near Florida City. And our Barrier Islands, which already have some problems, even with water level, will be flooded more frequently and will be cut by tidal channels, and the waves will be trying to cycle that sand landward. Warren Pilkey at Duke says for every foot of sea level rise, Barrier Islands will tend to migrate landward 500 to 2,000 feet. Of course, when you have condominiums in the way, that's a problem. Turkey Point nuclear power plant, whether it's the existing one or the new one, also will be out in Biscayne Bay. With a 4 foot rise of sea level, South Florida looks very different. Biscayne National Park and Florida Bay, part of Everglades National Park, are now one system. And we will have storm surges from both sides with a 5 foot rise of sea level. Our Barrier Islands should be gone. I don't know why I left them. We are so low, it's ridiculous. And the problem is that on top of what I showed you there, that was high tide, we have the storm surges like Rift of Boulevard Peninsula east of Galveston this year. And we have this is a 1.5 foot rise of sea level in Miami-Dade County this fall. That's what a 1.5 foot rise looks like at high tide, but that happened this year. So we get these anomalous tides. And the other problem is, not only the front side we have problems, the back side, the Everglades is low. Here's the bedrock area. The blue, dark blue is the areas that could be flooded by 3 and 4 and 5 feet of sea level rise if high tide could get in. Incredibly low behind it. And the problem is, there used to be a lot of organic matter, peat, build up in the Everglades, but it is gone. Basically, the white numbers show the thickness of the peat. And so as sea level rises, unless we rebuild that peat, seawater can just move right up and turn this very quickly into an Everglades estuary. If the Everglades restoration rebuilds peat, then we have the ability to help maintain a freshwater head, like your sponge you leave on the counter. It'll hold water through the night. But we may be able to maintain a freshwater head and not only maintain the Everglades longer, but also maintain our source of fresh water that we depend on down here. To finish, let me just say that one of the urgent things to do, and we've done it in Miami-Dade County, 3 different groups have taken high-resolution laser or airborne images of elevation called LiDAR and turn them into high-resolution maps. This is the baseline for understanding what you have. And this is critical to do because it turns out that a lot of areas are lower than you anticipate. But just look at Miami-Dade County with a 3-foot, 6-foot, and 9-foot sea level rise. We will be a severely diminished community with a 6-foot rise. And that's just high tide. These are very high-resolution maps, and they should be used to plan for infrastructure, utilities, where to develop, and also to make decisions about where we have to just give up and pull back. Okay? So the Earth has a close to catastrophic evolution of our coastal environments, habitats, infrastructure, coming this century. We have to get hold of this. Write down Jim Hansen. Go to his website, James Hansen. He's our leading climatologist. You can be put on his email list. He has all his writings. He sends out all his PowerPoints. You can study them and learn. He's always been right. That's why I recommend him. But he says we quickly have to get down from the trend we're on with CO2 and start pulling it out of the atmosphere to get down to where we were about in 1970, or it's over. Even then, we may have another 5-6 foot rise, but we have to do that. You know, it is just possible we could save the Everglades. I'm not sure about the Barrier Islands, but maybe Fort Lauderdale, Miami. But to do so, we have to act early. Understand it's not somebody else's problem. America caused this problem. We are the leading producer, and we still are per capita. These are the things we have to do. So thank you very much.
I think we're going to leave questions towards the end because I'm sure we can have a lot of questions here. I want to get back to one thing that Dr. Wong said, which was, why did we ask for the next decade? And part of that was because we always talk about these large increases in sea level rise, but our argument is that we need to do something now. And that's why we were focusing on the next decade. All right, our next speaker is Dr. Marguerite Koch. She is going to talk about climate change and marine ecosystems. She is a professor in the biological sciences at Florida Atlantic University. She hosts an active research program in marine ecology. She received her PhD from the Rosenthal School in Marine and Atmospheric Science. Was at Maritime with that one. An MS in Marine Science from LSU and a DS in Biology from Tulane. She studied coral reefs at Fairleigh Dickinson Laboratory at U.S. Virgin Islands, estuarine ecology at the University of Washington, and nutrient cycling at the University of Exeter, England. During her 25 years as a marine ecologist, she has worked across a broad range of habitats from the Bering Sea, Alaska, as a fisheries biologist, to the biochemistry of seagrass ecosystem in the U.S. Virgin Islands. Primary research interest is the sustainability and productivity of marine habitats, primarily tropical marine ecosystems living at the edge of stress tolerance. Research has led her to a keen interest in climate change effects on coastal marine ecosystems. Please welcome Marguerite.
Before I start my hand, a little bit taller than me. Well, I guess I don't really have to explain how important some of these polar regions are to South Florida, and even though that I'm going to be talking about South Florida, they're extremely critical, as Hal Wallace has just very eloquently discussed with us. Before I start, though, I want to make a caveat that actually most of the research on how marine as well as terrestrial species, communities, and ecosystems are going to respond to climate change is really in its infancy. We're really just starting to get a handle on how things are really going to change across these different scales. Today I'm not going to be able to cover, of course, all the different potential risks of a rapidly changing climate in marine systems. I'm not even going to touch on terrestrial ecosystems, and I apologize for those terrestrial ecologists out there. But I'm going to try to talk about marine ecosystems in a way that actually is across ecosystems, whether it's terrestrial or marine ecosystems. And I'm going to consider stress across the hierarchy of biological organization with a focus on South Florida ecosystems. Okay, so to this end, I should be able to quickly go over some of the physical science aspects that Hal already talked about. And I want to highlight some of the major stressors, though, that those will ensue, and consider stress at individual level, including mechanisms of resilience, which is an important aspect, at least under short-term, less drastic changes than Hal pointed out. And finally, put forth the tenet that we should really not take our eye off the forest for the trees, and really consider some of the ecosystem level responses to these major changes in current sort of environmental envelope, if you will, which a lot of these organisms evolved over longer periods of time, then we're seeing some of these changes so much more rapidly. And some of these ecosystem changes could actually be more like the Achilles heel if these tipping points or thresholds are reached. So I'm not going to talk about it, but again, this is probably the most important data set or slide in the world. And you should keep your eye on it. And again, Jim Hansen's recommendation that we really do need to get the CO2 levels down and support Hal's statement that Jim Hansen is definitely one of the people that really 30 years ago was telling Congress that they need to do something about climate change. It's been completely ignored for many years. As the climate has warmed over the last 100 years, the oceans have seen a corresponding increase in temperature, and this is important because we all know that water has a high heat capacity and can hold that heat for very long periods of time. Now, unfortunately, we're seeing this increase in temperature of different oceans across the Atlantic, Indian, and Pacific, as well as across latitudinal gradients. So this is not just something that's occurring in the northern latitudes. And we can see here that we're also seeing this change over time. You can see it across the latitudes, and you can see it going from blue lower temperatures to higher temperature. It's resulted in about almost 1 degrees C for the 20th century. Okay, I'm not going to go over this because Hal spent a whole lot of time on this, but pretty much the point here is that we're seeing an increasing rate. So if you take the sea level rise rates from 1961 to 2003, you can see it's a lot slower than 1993 to 2003. But over long term, again, Key West is sort of at this sort of average rate of change over long periods of time. Again, most of this is due to thermal expansion, and we haven't even really considered the Greenland and the Antarctic effect, which is what Hal was trying to make a point about. In addition to temperature and sea level rise effects, we have atmospheric CO2 that's actually being sequestered by the oceans. As a matter of fact, the CO2 concentrations would be twice the increase of what it is now if it wasn't been for the oceans and sequestering a lot of that CO2. So what we see is this increase in CO2 across different oceanic data sets. And the problem with this is it actually results in a decrease in pH. And although this pH doesn't seem like very much, maybe 0.1 pH unit, you have to remember pH is on a log scale, if you can kind of remember from your high school chemistry class. Thus, it's really a 30% increase in the hydrogen ion concentrations. And this affects something called the saturation state of carbonate ions or calcium carbonate precipitation. Now, when we think about marine ecosystems, a lot of times we tropical systems, we typically do think of like coral reefs. And it's important in terms for coral reefs to actually have the ability to precipitate out calcium carbonate. And what we see here is as we change we increase the CO2 concentration, so this is where we are today, we see this region in here which actually has what's called a high saturation state for precipitation of calcium carbonate. And that's actually a good thing if you're a coral reef and you need to build a calcium carbonate skeleton. But one of the things to look at here is you see how this saturation state changes. It becomes less ability for these corals to actually produce calcium carbonate. But the other thing to note is that we also have a difference north to south. So it's actually some of these deeper corals that don't feel cool.